Okay, so let's break the process down. Here's our ancestral stick insect, a 2%er, going to be giving rise to future generations, right? Now, in each generation, there's a struggle for existence. And if you'll notice, the 5%er here is boxed. This 5%er has a slight advantage. Now, why would a 5%er have a slight advantage over a 2%er or a 0%er? You'd think if it's sitting on a branch somewhere that a bird should be able to see a 5%er as easily as a 2%er. But birds are not always going to be in a great viewing position. There might be times when the viewing position is poor. Maybe there's low light, or the bird is far away or flying, and under those circumstances the 5%er just might escape detection, whereas the 2%er will be seen. So birds are going to be eating the 2%ers and 0%ers more often than the 5%ers. That means then that over time, the 5%ers will have the slight advantage, and that slight advantage can accumulate over time so that the 5%ers are going to be having more babies in the long run. Now, you'll recall David Hume had an idea that nature experiments when animals reproduce, and so we can think of, in Hume's terminology, the variation that we see in each generation as sort of the idea that nature is experimenting. Now, it's not that the parents, when they have offspring, are purposely trying to have different types of offspring. The parents don't have any say in the matter, but the nature of reproduction generates variation, and we can think of that as metaphorically like nature is experimenting with different animal designs. Some of those experiments yield an advantage in a particular environment. Other experiments are less advantageous. But remember, the way we're diagramming this, most offspring are inheriting the parental body type here. But each generation there is some experimentation, some variation. Now, let's say it this way, that reproduction experiments with different body shapes without regard to what would be best in a given environment, right? And for this reason, we say the variation that's produced each generation is random with respect to the needs or wishes of the insect parents, right? So the 2%ers here, they would love, knowing that there are predators in the environment, they would love for their offspring to be better adapted than they themselves were. But they don't have control over the reproductive process. So most of their offspring are going to inherit their body shape, which of course was good enough for them. They were parents, they survived to have babies. So most offspring will get the parental body shape. Some lucky individuals will inherit a variation that makes them a little bit better adapted to the environment. Some unfortunate ones will inherit a body shape that makes them worse adapted to the environment. So again, though, the ones who survive best here, they can only hope to have better adapted offspring. They cannot control the outcome. And so for this reason, biologists talk about the idea that this variation is random with respect to the nature of the environment or whatever the parents would want to have happen. Looking at it from the predator's point of view, we want to say that the predator is imposing a non-random selection on the prey. So from the predator's point of view, the predator sees some of the insects more easily than others. So the predator sees the 60%ers and the 40%ers more easily than the 80% stick insects, right? So this means that this is a non-random selection process. So while the variation might be random with respect to the environment and the wishes of the parents, the predator is imposing a non-random selection on the prey. Now think about it this way. If what the predator was eating was just random, then the predators would be eating the 80%ers and the 60%ers and the 40%ers, right? There would be equal chances of being eaten. But in reality, there are not equal chances of being eaten. The bird is seeing the 60%ers and 40%ers more easily, so eating these more often than eating the 80%ers. So in nature, there's an unequal chance of survival. And so we can say that the predator is imposing a non-random selection process. If selection were random, each would have the same chance of survival, but they don't. Now, it's also important to note that in this model here, that these insects, for each generation, they don't have to be perfectly adapted to their environment. After all, at this stage of this evolutionary process, we're only calling them 40, 60, and 80% stick-like, right? That's not 100%. The key is that in each generation, there's always some individual that is better than the competing body designs, right? So you just have to be better than your competitors each generation for this process to continue to operate. In this slide here, we see the concept of over time how the average body shape of the generation is increasing each generation. So in this case here, right, we've got 15 percenters, 25 percenters, and 40 percenters, but again, the 40 percenters will have an advantage, so they're going to have more offspring than the 25 and 15 percenters. Well, when they have offspring, the average body shape of the next generation is going to be higher than the previous average, right? And that's because it was only the 40 percenters that had the advantage here, and so they are going to be increasing the average body shape of the next generation. Now, it's also important to note that in its lifetime, take this 25 percenter here, it remains a 25 percenter over its lifetime. So its body shape does not adapt during the lifetime of this insect, right? Individual insects are not evolving. Rather, the population is evolving, right? The body shape is evolving, but each individual remains whatever it was at birth. If it was a 25 percenter, it will remain a 25 percenter until its death. And 15 percenters started out as 15 percenters, and they remain 15 percenters. So individuals are not evolving. The population is evolving. One way to think about this process of natural selection is the concept of sort of replacement or substitution. So here again, we got our 15%, 25, and 40 percenters. The 40 percenters have an advantage, and they are going to be having more offspring than the others. So in a sense, the offspring of the 40 percenters are substituting or replacing the offspring of the 25 and 15 percenters. And the reason for that is the 25 and 15 percenters are more likely to be dead, more likely to be food for birds. Right? So the 40% body shapes are replacing some of the 25 and 15% body shapes in the next generation. And this is then again causing the average body shape to increase its percentage towards looking more and more like a stick. In nature, this selection process is happening each and every generation. And it's the hereditary nature of these traits that preserves the useful variations, right? So the 80 percenters here, they have an advantage over the 60 percenters, and that 80% body shape, if it is hereditary, that is, if it can be passed on to the next generation, that's what's causing, right, the next generation to start out a little bit better adapted than the average of the previous generation. So heredity preserves the useful experiments, which can be improved in the future. Now we can think about that. We can see more clearly if we imagine what would happen if there was no heredity in the trait of body shape. So here we have the 40 percenter has the most advantageous trait. But if body shape was not hereditary, then the 40 percenters might have the following offspring. They could have 25 percenters as being the most likely offspring, with some 15 percenters and some 40 percenters added in, right? But the idea is that without heredity, this useful body shape is not going to be the most common in the next generation. You'll have the same type of variation as in the original generation. It's only when the body trait is heritable, can be passed on, that's why you get the ratcheting effect, why each generation has a greater and greater average body camouflage. And another important point, the birds here, the predators, the ones doing the selecting here, they are not trying to make insects better camouflaged, right? So there's, if anything, the birds would like the insects to be worse camouflaged. But it's just this natural interaction. When the birds are eating the ones they see, they are leaving the ones they don't see to reproduce, right? So there's no intelligent mind that's planning this evolutionary change. It's simply the interaction of predators and prey. The birds are not trying to make insects evolve better camouflage, and neither are the insects. They have no power to cause this evolution. They're just trying to get by and survive. But because the birds are selecting some to be eaten, they are selecting, in a sense, others to remain and repopulate the next generation. So we're going to define then the birds as when they are selecting, we can say that they're selecting better camouflage by eating the worst camouflage individuals. And over time then, better camouflage is evolving in the population, but there is no intelligence that's planning this process. It's just cause and effect, predator eating prey, and that's causing the population to change over time. Now remember, William Paley didn't understand how predators could cause changes in prey populations. He did not understand that predators were selecting individual members of the prey species. Remember, he thought it must have been God that created the adaptations of species and the nature of their interactions. And so, from Darwin's point of view then, the adaptations of stick insects today presents us with a kind of illusion. There's an illusion of design here. It looks like these creatures were well designed for a stick-like environment. But what we don't see are all the past failed experiments in the long history of evolution of this species. So when we come upon a well-adapted species, it's natural to think, wow, look at these adaptations, and maybe there was some intelligent mind that has designed these adaptations. Darwin's argument was that's kind of an illusion, because we fail to see all of those not so well adapted individuals of each generation that were food for the predators, but that was causing this evolutionary process to happen. And so in the past, there were insects that didn't look much like a stick, but over time, natural selection can cause this population to evolve better and better camouflage, and today we see the result of that long evolutionary process.